Okay, it looks like everyone who was in the process of joining has now joined. Again, my name is Pam Pearson. I am the director of ICCI and the chair of Arctic 21. And as I noted with a little bit tongue in cheek, we actually this time are focused entirely on the Arctic for this particular meeting. It's been a while because there's been so many things, especially happening around Antarctica. But we're very lucky to have a very timely presentation from Alexandra Jahn, the lead author of the recent Nature paper that was talking about projections of the state of the Arctic Ocean, Arctic sea ice, with different emissions trajectories going forward, both in terms of time and in terms of extent. So without further ado, Alexandra, please take it away. She is at the University of Colorado Boulder. And I don't know if you're technically part of NSIDC as well, Alexandra,
Nope.
but I'll leave that for you to clarify.
Okay, yeah, thank you very much, Pam, for the introduction and the invitation. And yeah, I'm in the Department for Atmospheric and Oceanic Sciences and the Institute of Arctic and Alpine Research at the University of Colorado Boulder. We also have NSIDC, the National Snow and Ice Data Center at CU Boulder, but yet that is yet another institute. And I think no one who's not at CU Boulder understands all the different institutes and how they're related. Yeah, I'm excited to be here today to talk about our recent review paper in Nature Reviews Earth and Environment. Put the free paper access link up there, and the QR code takes you there as well, since otherwise it's behind the paywall. This is work that I did with my co-authors Marika Holland at the National Center for Atmospheric Research in Boulder and my colleague Jennifer Kay at CU Boulder. And before we start talking about an ice-free Arctic, just want to quickly talk about the observed Arctic sea ice decline that we've seen to make sure we kind of know where we're at in this transition towards an ice-free Arctic. And so this is showing the Arctic sea ice extent, so the aerial coverage of Arctic sea ice based on satellite observations that go back to the late fall and early winter of 1978. And it's color-coded, so the darker colors are longer time ago, and then the yellow-green colors are the more recent years. And we can see that we have lost sea ice in all months of the year. The yellow colors are well below the dark blue colors at the beginning of the satellite record 4 decades ago. And we've seen that in all months of the year, but we've seen the largest decrease in September, which is also the seasonal minimum in the Arctic sea ice. We've seen this large decrease in September because that seasonal minimum kind of integrates the changes that we're seeing throughout the year. Because if we have a delayed start of the growth season, or reduced growth during the winter time, or enhanced melt during the melt season, that all gets integrated into the aerial sea ice coverage at the end of the melt season in September. And so September is the months that, as Arctic scientists, we tend to look at the most, not because it's the only month there's anything happening, but because it has the largest changes, and also because it is the minimum. And so if we're looking at reaching ice-free conditions, obviously that will happen first in the months where we seasonally have the lowest extent in sea ice. So if we look at the time series of the observed sea ice loss going back to 1979, in September, we can see that we have a very clear decline of sea ice, but also a lot of interannual variability that is superimposed on that. We just focus on the decline overall. We've lost about 3.5 million square kilometers of aerial sea ice coverage in the Arctic since the beginning of the satellite record. And that's about half of what, so we still have about half, or we lost about half of what the sea ice used to be at the seasonal minimum. And 3.5 million square kilometer, I always like to put that into context because it's not something that anyone really is intuitively maybe familiar with. So it's equal to all the red colored states here. So it's a huge area of sea ice that we have lost at the seasonal minimum, and slightly smaller areas that we've lost throughout the rest of the year. And so it's a very large area that used to be covered by sea ice and is now open ocean at the end of the melt season. And this loss of sea ice over the last couple of decades has been very clearly a result of anthropogenic climate change. And many papers have looked at that. And so just kind of quick look at two of those, which have also shown that it's not just forced by climate change, but there's actually a very strong linear relationship between the September sea ice area and the global temperature increase, based both on observations, which are the black dots here, and then on the variety of climate models, which have similar linear relationships. And similarly, also sea ice area is linear related to what's driving the global temperature increase, the cumulative CO2 emissions. And again, we see that in the observations, and we see that the climate models show that as well. And so what this linear relationship tells us that more CO2 emissions, more global warming means less Arctic sea ice area. And so then it's not surprising that the projected future sea ice loss is that under all future emission scenarios, it's predicted that there will be a further decline in the Arctic September sea ice area in the future. Under all the scenarios that are being looked at as part of the CMIP6 model intercomparison project. And all the models agree that there will be a further loss in the sea ice area in the future. Sea ice is different than some other variables in the climate system in that it is zero bound. So at some point we get to zero and we cannot lose any more sea ice. And so that's what's shown in this figure here too, as the practically sea ice free. And so that's going to be the main point of the presentation, looking at when are we going to reach practically ice-free conditions and what does that mean? So what is an ice-free Arctic? So in 1979 or in the 70s in general, this is how the Arctic looked like in September at the seasonal minimum. So it was really a white Arctic year-round with sea ice covering the majority of the Arctic Ocean, even in the summertime. And then in the wintertime, it was even more extensive, reaching outside of the Central Arctic Ocean basin. And a practically ice-free Arctic looks like this picture over here, where there's still a tiny bit of ice. That's why this is practically, but the majority of the Arctic Ocean has no ice anymore. And so it is ice-free for most purposes. And so this threshold that is used for that is commonly 1 million square kilometers. That is equal to practically ice-free, and that's what's plotted here. That's what 1 million square kilometers of sea ice remaining looks like, and it's always found in this region here, which has also been called the last sea ice refuge, where sea ice will persist longer than anywhere else in the Arctic. And this transition to an ice-free Arctic is really a regime shift in terms of the physical properties of the Arctic from this perennial sea ice cover where we have multi-year ice in the Arctic to a seasonal sea ice cover where all the ice is first-year ice, thinner ice with different physical properties. And it also marks the end of this ongoing transition where we're already halfway between these two states, from a white summer Arctic to a blue summer Arctic. Right now, we're kind of in an intermediate state where half of the Arctic is already a blue summer Arctic and the rest is still covered by sea ice. Why does an ice-free Arctic matter? So there's really a lot of implications, and they don't just all happen only when we get right to an ice-free Arctic, but their amplitude is often amplified the more we get towards this ice-free Arctic, but we're already seeing many of those. One of them is the impact on the Arctic ecosystem, in particular species that are adapted at the ice cover in the Arctic, like the polar bear. That's kind of become the poster child for climate change in the Arctic because it depends on sea ice for hunting, but also the seals. And as we know, ecosystems are always very closely coupled, and so kind of a disturbance to any one part of that has repercussions throughout the system. There's also lots of impact predicted on the fish species in the Arctic and the phytoplankton due to changes in the light availability when the sea ice is gone. That also impacts the people that live in the Arctic and that depend on subsistence hunting of these large mammals, as well as on sea ice for travel between communities. There's also a lot of interest in shipping through the Arctic to cut days off the ship journey from the East Coast or Western Europe towards Asia, especially going across the Arctic here in the Green Line, which stays primarily in international waters. There's a large impact on the climate system through this transition of from a white Arctic to a blue Arctic, because that affects how much of the incoming solar radiation in the summertime. When we have a lot of solar radiation in the Arctic, we have 24 hours of sunshine during parts of the summer. And so a lot of that solar radiation used to be reflected 80%. And if the Arctic is blue, open water, only about 10% get reflected. So 70% more gets absorbed. And that has impacts on the Arctic itself, but also on the heat fluxes in the atmosphere and the ocean into the Arctic. And that can have repercussions on the mid-latitude weather. There's also implications again to the people living in the Arctic, because when the Arctic was covered by sea ice, the waves were kept relatively small and away from the coasts. And we have already seen a lot of increase in coastal erosion around the Arctic coastline, because the sea ice retreats further for longer. That leads to larger fetch, which makes bigger waves and leads to more coastal erosion. And so several communities had to be relocated, and several more will have to be relocated to adjust for that shift in the coastline. And so a lot of these are ongoing, but they will get amplified the more ice we lose, the more close we get to an ice-free Arctic Ocean. So what are the CMIP6 projections of a first ice-free Arctic? So this was a review article where we kind of look back at all the published studies, but then also reanalyze some of the existing data to kind of come up with a best estimate of when we can expect to see a first ice-free Arctic. And so this is showing the probability of ice-free conditions in terms of the IPCC ranges of likelihood under the different scenarios, from the light blue with the low emission scenario to the red being the highest emission scenario. And we can see, as shown by this red line here, the 66% or likely threshold is going to be crossed before mid-century, sometime in the 2040s, based on these projections. And so that means first ice-free projections are likely to have occurred by mid-century under all the CMIP6 scenarios, the low, medium, and high emission scenarios. And they could occur as early as the late 2020s and 2030s, getting more and more likely the more time goes on. We can see in the 30s, we're already in the as likely as not, and then getting into likely and very likely after mid-century. And that was looking at monthly data, and all prior projections of ice-free conditions were based on monthly conditions. However, the first time that we will actually observe an ice-free Arctic and have a satellite picture rather than just a model output or AI-generated image of an ice-free Arctic will be observed from daily satellite data. And so we also looked at how much earlier will that happen? And so based on one climate model with 50 members, we found that in 56 of these simulations, 56% of these simulations, we had daily ice-free conditions occur earlier than monthly. And so this is showing this offset, how much earlier daily ice-free conditions occur in years compared to the first year that monthly ice-free conditions occur. And in 20% of the members, which are these ones up here, we see that this offset is larger than 10 years, with an average of about 4 years. And so daily ice-free conditions, just individual 1 or 2 days, will happen before monthly ice-free conditions in about probably about 50% of the cases. They could happen the same year, but they could also happen significantly earlier, with the largest offset being 18 years. So that's about when we expect to see first ice-free predictions. But for most implication, the most important thing is how frequently we can expect ice-free conditions. If it just happens once, it's novel, but it's not going to have these big implications. Whereas if it's something that becomes something that happens year after year, has many more implications. And so here we're looking at the frequency of September ice-free conditions, or the probability of ice-free conditions in a given year, based on these same model simulations and the same scenarios. And we can see very clearly that while for the first ice-free Arctic, it wasn't dependent on the emission scenario, we have a big impact of future emissions on how frequently the Arctic will be ice-free, with 100% probability of ice-free conditions in September starting in 2060 based on the high emission scenario, very likely after 2070 in the SSP 245, and then actual decreasing probabilities after a certain point in time for the two lower emission scenarios that have decreasing temperatures, some point during the 21st century, and then sea ice recovers, and so the probability reduces. We also have a big impact of future emission scenarios on the lengths of ice-free seasons. So everything up until now, we just looked at September. And as I said, that's what we first look at, because that's when we reach ice-free conditions first. But ice-free conditions are not just limited to occurring at the minimum in September. They can occur in other months of the year. And we can see a big difference, again, between the different scenarios, from the low emission to the high emission scenario, of how long this ice-free season, this blue Arctic, can last potentially. We can see that under the lower emission scenario, there's a possibility of seeing it potentially 3 months of the year, but it's unlikely outside of September. Whereas even under the SSP 245, by the end of the century, we have 3 months of virtually certain ice-free conditions in August, September, and October, with an additional possibility of seeing it for 2 more months. And then under the SSP 585, the worst case scenario, we're looking at 5 months of guaranteed ice-free conditions, with very likely for 6 months, so half a year of ice-free conditions, which would be an entirely different Arctic than one that has ice-free conditions occasionally in September or maybe August, like we would look at under the SSP 119. And we can look at that spatially as well to kind of see like the difference in what the Arctic will look like. So this is showing the year of consistently ice-free conditions. So the year after which it is more likely than not, that the Arctic will be ice-free in a given location. And we can again see the different emission scenarios here for the months July to November. And we're looking at very different Arctic's sea ice covers under the low emission scenarios, where we can see that ice-free conditions are really primarily happening repeatedly only in September. And we have large parts of the Arctic that would be ice-free that currently are still ice-covered by the end of the century. But we still would have very ice-covered, for example, November and July. And so it would really be a late summer phenomena. Whereas if we look at the SSB 585, we have absolutely no ice left anymore at the end of centuries for these 5 months, as I just showed you. But I think just looking at that spatially is just another way of kind of really understanding how different these different Arctics will look like depending on future emission choices. So with that, just want to summarize: Arctic sea ice is declining due to anthropogenic climate change, with the aerial September sea ice cover already reduced to about 50% of what it once was in September. Practically ice-free conditions of less than 1 million square kilometer of sea ice area are predicted to occur under all emission scenarios. And the first monthly mean ice-free conditions may occur as early as the late 2020s or 2030s, and are likely to occur by mid-century. Daily ice-free conditions will precede monthly mean ice-free conditions and could occur 10 years earlier. And future greenhouse gas emissions will determine how frequently ice-free conditions will occur and for how many months a year they may occur. There's a very big difference in what kind of future Arctic Ocean we will see at the end of the century. And with that, I'd be happy to take any questions.
Thank you so much. This was a really excellent presentation. I'm going to open it up for questions right now, and I will ask the first one with the group's permission. In climate world, although a lot of certainly negotiators know can talk SSPs and RCPs, there's a lot of focus on the peak CO2 and or temperatures. And so I don't know if you're able to speak to the ways, say, that Julianne Strove and Dirk Knotts have put this in terms of CO2 levels or temperatures, where, for example, you're looking at say around 1.7 is when you might have a brief ice-free period every year. Although I will say that Julianne in Dubai noted that with the past few years adding those in, it's looking more like 1.8 rather than 1.7. So that's a moving target because things are changing quickly.
So I'm not 100% sure. I would have to go back and look those up, like what are the top temperatures that they pop out at, but that's kind of, so we looked at that in the paper too, and looked at the probability of ice-free conditions in terms of global mean temperature. And that was a 5-year mean, so not like a climatological 30-year mean, but like a 5-year mean temperatures. And so we can see how the probability increases, and it kind of reflects some earlier work where we also looked at under the Paris protocols, can an ice-free Arctic still be avoided? And there was a small chance of avoiding it if global warming was limited to 1.5 degrees or less. And we see that here again. And then the probability goes up very high as soon as, like here, we're getting to 2-degree warming. We're in the likely to very likely range. So that kind of similar to this earlier work, showing that if warming stays below this Paris Protocol's goal of less than 1.5 degrees, there is a chance that it would still happen just due to internal variability, but it wouldn't happen very often. We looked at that, the probability, like it would maybe happen every 40 years, so it'd be a rare event rather than something that happens year after year. Once we get to 2 degrees, it becomes something that is likely to happen every second year or more frequently than that. And so it's a very narrow range in terms of in September reaching ice-free conditions. But as we see also for in terms of this frequency, the less warming, the better. So it's not just binary, it can't just be 1.5 or 2. Anything in between is also better. We maybe then will only see an ice-free Arctic every 5 years or something like that, if it's as yeah, and things like that. So, but this also kind of shows the temperatures that we're getting to in these simulations by 2100. So, yeah.
And of course, I think that your later slide in terms of what the Arctic would look like under these different SSPs was very telling as well.
Yeah.
So yeah. Other questions?